Now let's talk about matrix vector multiplication. This is a very important concept, and this one requires actually spending more time on it. So for a vector matrix multiplication, consider a general case that A is m by n, and then x is a vector of n by 1, n-dimensional vector. And then y, in a sense, so when you multiply m by n matrix by n by 1, so first these two dimensions should be the same, and the resulting vector should be is m by 1. So y is m by 1. See, these two should be the same, otherwise you can't even multiply them. Then the result should be m by 1. And that's what I say here. So x is n by 1, y is m by 1, and a is m by n. Or in a sense, y is m-dimensional vector, x is an n-dimensional vector, and a is a m by n matrix. Okay. So first, let's see what we can drive for the ith row of vector a. What's the expression for ith row of vector a? So let me just now here write x1, x2 all the way to xn, and then let's use uppercase a11, a12 all the way to a1n. Here we have a m1, a m2 all the way to a mn. So this is equal to what? This is equal to y1, y2 all the way to ym. So remember, y is m-dimensional. So what is it equal to? The ith row of y, we are looking for that, is equal to multiplication of the ith row of a by this column vector x. Well, what's the ith row of a? We talked about that. The ith row of a is nothing but ai1 means the first index is I, ai2 all the way to ai n, and that's what I have here. aik you multiply by xk. What do I mean by that? Means that you multiply ai1, this element, ai1 by this x1, ai2 by this, and all the way to ain by xn. So that's one way to define yi. But what is this? Remember the lecture on video, on vectors and the dot product of two vectors. This is just exactly the definition of dot product. Remember, I defined them, for example, y to be A transpose B. I said y is equal to what? AI bi. This is exactly the same thing. So one way to define a matrix vector product is to define it in terms of dot product. What do I mean by that? This means that take the ith row of A as bi transpose, right? What do I mean by that? Take this ai1, ai2 all the way to ain as bi transpose. Then you can calculate each component of vector I or each row of vector I as follows, as this dot product operation, right? You can say yi is equal to bi transpose times x, right? So remember, we define the vectors usually in terms of column vector, and that's why we define it as a bi transpose, because this is a row vector. So this one is ith row of A. So one way to define a matrix vector product is to define it in terms of a dot product of two vectors. Dot product of column rows of A and the column vector x. This way is good. It gives you some intuition. Later on, we talk about orthogonal matrices, or we talk about what happens when the rows of matrix A are orthogonal to the vector x. We talk about all this, but it's not really intuitive this way. What do I mean by intuition? I mean, you can get more information from matrix vector product if you define it in different way. What it means is that let's again write matrix A as a11, a12 all the way to a1n. a21, a22, all the way to a2n, and then all the way am1, am2, all the way to amn, and then you have x1, x2, all the way to xn here. So let's just multiply them. Let's see what you get. So what you get, how do you multiply first? You multiply by this, multiply by column vector x. So this is going to be a11 x1 plus a12 x2 all the way to a1n xn. This is going to be a21 x1 a22 x2 all the way to a2n xn. And then we have am1 x1 am2 x2 amn xn. Okay, so this is the resulting vector. Remember, this is m by n vector. M by n vector. Now, let's study this vector for a while. You see, this x1 is the same. Here, the first component has x1. If you get rid of x1, what you get is the first column of A. Now, what was the first column of A? Is a11, a21, all the way to am1. That's exactly here, a11, a21, all the way to am1. So you can, in a sense, write it like this: x1 times a11, a21, all the way to am1, plus x2 times the second column, all the way to xn times the nth column, the nth column of A. And that's what this one says. Remember the definition we had for a block vector, and then as a void matrix, as a tall matrix, we talk about this AI as the ith column of A. So A is exactly the same thing I explained here. x1 times the first column, x2 times the second column, all the way xn times the nth column. So that's a very intuitive definition. What it says is that you can consider the matrix vector product as a linear combination of, I have here, as a linear combination of column of A. Okay, so you can consider the matrix vector product as a linear combination of column of a matrix. So remember this definition, we're going to get back to this definition shortly, actually, when we talk about the linear independence and the basis vectors. So now let's talk about some example for the matrix vector product. So I would say example here. If A is 0, 0 matrix, then AX is 0, right? You can use any definition you like. Let's use this intuitive definition. Regardless of what is X, if you use every column of A is 0, so linear combination of 0 vectors all 0. Okay. Now, identity. If A is an identity matrix, then AX is equal to X. Let's look at this. There are many ways to look at that. You can actually multiply them. It's very easy. Identity has only one per each row, right? So multiplication is easy. But if you look at that in terms of the linear combination of the columns, right? So what is the identity? What's the column of that? 1, 0, 0, then 0, 1, 0, right? So in a sense, you would get x1 plus x2. What does it mean? What do I mean? You would get x1 times 1, 0, 0, 0 plus x2 times 0, 1, 0. What are these? This is each column is the unit vector. So this is the E1, the unit vector for the first dimension, right? So it has a 1 as a first component and 0 otherwise. This is the unit vector for the second coordinate, and all the way you get plus xn times unit vector for the nth coordinate. En. Okay. So remember we said that we can represent any vector as a linear combination of the unit vectors. This is exactly the same thing. So all you are doing is you're representing vector x as a linear combination of its component, right? So you can represent vector x as a x1 times e1 plus x2 times e2 all the way to xn times en. And that's why the answer is x. Or you can also go ahead and multiply that. So the linear combination of the column of A is actually the vector x back, because you can represent any vector as a linear combination of the unit vectors. So another example is that if you take the x to be actually the unit vector, let's say ej. Ej means that the jth component is 1, and then the rest of them is 0. The jth position is 1, the rest of the elements is 0. So A times ej picks up the jth column of A. Why this is the case? Why is this the case? The best way to look at this is, the best way to look at that is by looking at the definition of matrix vector product in terms of linear combination of columns of a matrix. That's the best way to look at that. What I mean by that is A can be anything. A can be anything, right? But X is EJ. What does it mean? When I say X is EJ, what does it mean? EJ. So I have it here actually. It means that the jth location is 1. So how do we represent A times EJ? We say that is equal to 0 times A1. A1 is the first column of A, plus 0 times A2 all the way plus 1 times AJ plus all the way 0 times AN. A has n columns. The rest, all of them are 0. The only thing that is not 0 is AJ. 1 times AJ, which means the jth column of A. So if you want to pick the first column of A, the jth column of A, if you want to pick the first column of A, what should you do? You have to multiply by the E1. If you want to take the 10th column of A, multiply by E10. E10 means the 10th component is 0. The 10th element is 0. That's what it means. Okay. So now here I talk about this in terms of a transpose, and in terms of all these. What I'm talking about that here is what if you want to talk about that in terms of transpose of a matrix. The idea is the same. You can take A transpose to be B, right, where B is n by n matrix. Okay, so the idea is the same. Now A transpose times EI, it takes the ith column of A transpose, right? It takes the ith column of transpose. As I said, you can define A transpose to be B. It takes the ith column of B, right? So this is easy. But then you talk about the transpose and the properties of a transpose. So let's look at this. A transpose EI is equal to I will gonna show it as BI, but BI is the ith column of A transpose, right? Because AI I take it as a ith column of A, so I'm gonna show this one as BI. Now I'm gonna go ahead and take a transpose from both sides. That's what I'm gonna do. Let's see what's gonna happen. Take transpose from both sides. You're gonna get what? If you take a transpose from both sides, you're gonna get A transpose EI transpose is equal to, what's gonna happen? We're gonna get the ith row of A, right? You're gonna get the ith row of A. See, the ith column of A transpose becomes the ith row of A when you take a transpose. So if you want to take them ith, the second row of A, the second column of A is very easy. You just go ahead and multiply by E2, easy. But what about the second row of A? What you do, you're gonna go ahead first calculate A transpose, right? And then multiply by E2 and then take a transpose. Okay, so for example, A transpose E2 transpose give you the second row of A. Okay, that's very important to know that, to be very fluent how to get the ith column of A, how to get the ith row of A. So getting the row is a little bit more complicated. Remember, getting a column is easy. You just go ahead and multiply by unit vector of AEI, for example, getting the ith column. Now, column and row have some sort of notion of the transpose involved. So you're going to go ahead and first get the ith column of A transpose, then you transpose this one. Okay, good. Now, what if the vector x is one vector? Remember, we defined the one vector as a vector whose all the elements is one. So what if I have this? Then if you write A as it is, and then you multiply by the vector 1, what's going to happen is that the first row times the vector 1 is going to be A11 plus A12 all the way to A1n, right? So sum of the first row, sum of the elements of the first row, then all the way to sum of the elements of the mth row. So if you want to get the sum of the elements of a row, all you need to do is just go ahead and multiply a matrix by one vector. Okay, so there is another way to again think of this problem is by looking at that as a linear combination of the column of A. So when you multiply a matrix by a row by one vector, this means that what you are doing is this: 1 times A1 plus 1 times A2 all the way 1 times AN. So you are adding the columns of a matrix. You're summing all the columns of a matrix, right? That's what it happens. Which another way to define that is that you're getting the sum of the first row, then sum of the second row, all the way to sum of the mth row of matrix. So there are different ways to look at the matrix vector product. So this is again here I said as a linear combination of the column of A. I'm talking about getting an average of the column of A. So remember, when you multiply by the one vector, you get the sum of the columns of A. But what if you go ahead and multiply by A by 1 over n? You multiply A by 1 over n. What is 1 over n vector? 1 over n vector x is 1 over n is this. 1 over n, all the way 1 over n. So go ahead and apply this definition of linear combination of column of A. So this is the same. Here, each one has a weight of 1 over n, right? So you can factor from, let me not write it down, let me write it here, right? So here, you will have each one 1 over n, each one 1 over n. So you're going to get 1 over n sigma ai, average of column of A. So you can actually play with this stuff. You can get the average of columns of A easily. Just go ahead and multiply matrix A by a vector whose all the elements is one vector. Okay, good. Now let's talk about the properties. So when you have A plus B, which each of them is m by n matrix, multiplied by a vector U, you can actually multiply vector U first by matrix A, and then by matrix B, and then add them all together. That's what this one says. Right? You can multiply this by this, and then this one by this, and then add them all together. When you multiply a constant by AU, which A is a matrix and U is a vector, you can multiply a constant by either of them first. You can first multiply a constant by a vector, then the resulting is still a vector, and then multiply that matrix by that resulting vector. So it doesn't really matter.